Okay. Uh, as I mentioned last week, and probably have mentioned at least a couple of times before, the the data that you deal with kind of drives uh, well the nature of the question to a certain extent that you want to answer, and plus the data that you deal with kind of drives the analysis. And in sort of working with quantitative data, when we have nothing but quantitative data, like the predicting the GPA alpha, the SATs, or predicting a weight off of BMI, or seeing if there's a connection between those things. What we end up doing is using correlation to see if there's a connection. And correlation only speaks to relationship. It only speaks to the strength of relationship. It doesn't speak to any sort of cause and effect. So if there's nothing causative there at all. And then when we wanted to predict one quantitative variable from another quantitative variable, or more than one other quantitative variable, we always used regression, because it was a predictive function. Now, it does, once again, it doesn't talk about causation. It doesn't talk about cause and effect. It just says, okay, these two things, or these multiple things, are related, and we can use one to predict the other. If we know one, we can predict what the other might be. And if you remember, the caveat always was there that the prediction is based upon group data, and so it becomes very difficult to use the function that you generate, or the function you derive, that regression equation, to predict individual students or individual patients' outcomes. And so, there are at best relational and predictive. And, that was the thing that the modern scientific method improved on, which was a way of, at some level inferring causation. That if we had an experimental group and a control group, and they were random, and we did different things to them, then we could talk about causation. Now, we could only infer it. We can never be 100% sure. We can never make sure that we were 100% sure, but it allowed us to talk a little bit in that language. And so that becomes the language of the modern scientific method. But a lot of things are purely best explained, or purely best dealt with, as either looking at relationships or looking at predictions. And well, let me get over on my little handy dandy visualizer here, and slide y'all over on the other side, since I'm right-handed. One of the, when we talked about early on in the mix here, we talked about that statistics was a matter of looking at error, looking at measurement error, and looking at the difference between error that is related just to randomization, and error that's related to some sort of systematic influence, as if there's another factor or something that's somehow disturbing things a little bit. And we always had kind of a formula here that kind of on top of whatever it was that we're looking for, whether it was a z-score or a t-test, or anything, that any sort of statistic we're playing with, on the top of it we would have some sort of comparative. And for example, in a paired t-test, it would be pre-test minus post-test. That would be the comparative. In a traditional scientific methodology, experimental method, we'd have a difference between a mean for the control group minus, or excuse me, a mean from the experimental group minus the mean from the control group. And so there's always a comparative on top. And the thing that we put on the bottom is the random error estimate. and that's always on the bottom. And so there are these two elements that are in any sort of a statistical any sort of statistic, and that is the comparative on top and the random error on the bottom. And so we are comparing, observed error with and finding the ratio of that with random error. Now, what we use for random error is different based on the methodology. For z-scores, it's standard deviation. For t-test, it's standard error of the mean, or standard error of the difference, or it's a different standard error, but it's the random error measurement. It's actually called an unbiased predictor of random error. And so we always have those elements there. And with ANOVA, we have, the error that we don't find within groups, in a ratio to the error that we find, what we would predict to see otherwise. And so we're always looking at a comparative as a ratio to a random error. So what do we do when we get to categorical variables? Because categorical variables, we can't find the means. We can't, there is no mean. You're just in one group or the other. And so we don't have a way of thinking about, under the old model, how do we get to build some sort of statistic that will allow us to compare different, to see if a couple of categorical variables are related. And so we have to fall back on something else, and what we fall back on is probability. And probability, and it's closely related fraternal twin odds, are ways of talking about how likely something is to occur. So let's say I flip a coin, and heads or tails. Well, the probability of either one is 50%, but the odds are 1 to 1. In other words, if I'm predicting heads, I got a 50% chance of getting it. If I'm talking about odds, that means for every heads, there's also a tails. So it's 1 to 1. Let's say I'm rolling, I'm rolling a die, a die, and it's got 6 numbers on it, 1 through 6. The probability of getting any one number is what is probability of getting 1 through 1 out of 6 is 1 divided by 6. So what is that? Is that 0.18 or something like that? So there's about an 18% chance. I should know this. I used to go to the casinos every now and then, but it's about a 17 or 18% chance of getting any one number. And so if you think, okay, I need a 2 or I need whatever, there's about a 17 or 18% chance you're going to get that number. But the odds of getting any particular number are 1 to 5. Because there's 6 outcomes, I want one particular outcome, that means there are 5 other possible outcomes. So the odds of it would be 1 to 5. And so odds and probabilities allow us to understand the likelihood of things occurring. And so we can use probabilities as a way of determining the error term that goes on the bottom of this statistic. And we can simply do a comparison between what we observed and what we expected as our comparative. And so if we have two, let's say we're looking at the example where we're talking about kids that participate in sports and whether they graduate from school or not. And let me just create kind of a quick little example here. It's a 2x2 table. And then we'll look at an example on JASP. And let's say that we know in our school that about 30% of students participate in do not participate in sports, and it's one of those highly competitive schools, and 70% do participate in sports, and we have about 10% of the students that from 8th grade through senior year don't end up graduating, and about 90% that do. And this is a very high performing school, a very competitive school. So if I were to hypothetically say, we've got 100 students, random 100 students, what would I predict that would be in each one of these categories? And there's a simple formula there. It's the row percentage times the column percentage times the n. And so, up here, I would expect, I'll use E for expected, 10%, so 0.10 times 0.3. And so I would expect times 100, 3 students to not participate in sports and not graduate. If I look at students that didn't graduate and participated in the sports, 10% didn't graduate, 70% participated in sports, so the expected outcome here would be 7. 0.1 times 0.7 times 100 is 7. And if I go down here to kids that didn't participate in sports and graduated, I would be 0.9 that graduated, 0.30 that didn't participate in sports, so 0.3 times 0.9, 0.27 times 100, so I expect to get 27 in here. And kids that did participate and graduated, 0.9 times 0.7 is 0.63 times 100, so I'd expect 63 in here. So if I were having things occur purely by probability, purely by random blind probabilities, that's what I would see. Now, let's say I go in and I actually pull 100 folders. I pull 100 folders of students that had been in the same school from the 8th grade through their senior year. So I pull 100 folders. And I find that this is the case. That when I observe, I discovered that people that didn't participate and didn't graduate, there were actually 8 of those. I find that people that did participate and didn't graduate, there were only 4 of those. I find that of people that did participate in sports and did graduate, that there are 70 of those, and I find of people that didn't participate and did graduate, there are, let's see, do my math here real quick, 12, 82, 18 of those. And so what I find is possibly at odds with what I would have expected to find, but how do I know what might be happening here? Well, we can make a kind of a leap of faith here, use the same model. And so on the top of this particular statistic, which we're calling chi-square, on the top of this statistic will be a comparative, and the comparative will be observed minus expected. And on the bottom, the comparative would be expected. Now, I have to do some finagling here. You know, I have to, if we just do observed minus expected up here, we're going to sum to 0 because there was 100 observed and 100 expected. And so we have to square these things up here. And since we've got 4 cells, I have to sum across the 4 cells. Or, excuse me, I have to sum across each cell, all 4 cells. And that's chi-square. And we'll talk about regression, logistic regression in just a second, because that's actually, you have dealt with something that's very familiar to that, and that is regular regression. Any question before we look at an example? Okay, give me just a second here. All right, let me pull up and share out with you the JASP I just opened. Now, this is this is the JASP file that you'll be using for the final. As I say, I've cleaned it up a little bit and I've made some, changes and things. And so you'll see some things that are a little bit different than what you saw on the example, but you should be able to follow it along pretty well. In order to do chi-square, we have to first start with a frequency, and we have to create what's called a contingency table. And so a contingency table is essentially a crosstab table. And so I'm going to put marital status in this, and I'm going to ask the question, is marital status related to whether you have ever been booked into jail or not? Now, it doesn't say whether you've ever been convicted or not. It just, has it ever been the case that you've ever been booked into jail? And is marital status related to that? The default statistic is already chi-square. So we don't need to do anything to the statistic. In the cells, we would like to have the expected value because that helps to understand what's going on in the cell. And so we'll put the expected value in these things. And that's really all we need. And then we have this outcome table. We know that the chi-square is less than 0.05. The p-value is less than 0.05. So this is a significant relationship. This is a significant relationship. Now, what we end up having to do is to look at the changes, the differences, discrepancies, whatever word you want to put on it, within the cells to get to kind of understand where things have happened. And, you know, the expected value, say for this cell, booked. Now, you may ask, why is it 0 and 1? Some procedures on categorical data require them to be directional. One is the case that we would say, you know, you haven't been booked, so you wouldn't answer in a positive way, or 0. One is that you have been booked, so you would be different from the status quo. And that creates a directional outcome for this analysis. But if you looked at these, you know, marital status, now we have to go back and look at the book on marital status. And I'm thinking that, anybody here, did you look at the scale on that? Have you looked at the scale on that? It seems like 1 is married, 2 is, you know, perhaps never married, 3 is divorced. I mean, there's different categorizations here. But if you look at this, let's look at one cell here. Let's look at book 0, marital status 1. We expected 57 people in there. We had 63. For marital status 1 having been booked, we expected 28 people in that cell. We had 23. And so in one area here, we had more than we thought. In the other area, we had less than we thought. And if you go through the whole chart and kind of look at what's going on there, you'll see that down here, you know, it's nothing really changes very much in, say, level 4 of marital status and booked. It's pretty much what we have predicted. 3, which I think is the divorced notion, you know, once again, the count's higher here for being booked and lower for not being booked. Not married ever, the numbers are so small it doesn't really matter. And so we can begin to think about what's going on here. People that were married, if this means married, if 1 means married, people that were married were less likely to be booked than we would expected purely by chance, as were people that were divorced, which I think is 3, were more likely to be booked than we would have thought. and less likely to be booked, less likely or not to be booked than we would have thought. And so it looks like that marriage has some sort of relationship to likelihood of being booked. Questions? Okay. All right. Well, let's look at logistic regression. I'm just going to run it on the same data, and we'll use some of the same notions here. Since we know booked is 0 and 1, let's see if we can figure out if, for example, what else can we? Let's see if ever having had high blood pressure and marital status together, we'll put both of those in there just for the heck of it. Let's see if, and sexual identity, or we'll use gender. This is actually our sex is gender. And so we will use regression. We pull regression down. You'll notice there is a logistic regression in there. Logistic regression is simply means that we're we're converting categories into log functions and running a regression using log functions. So don't worry about that. You have no earthly need to know that. And so we'll put booked in there again as a dependent variable. We will see if gender and I don't know, ever having high blood pressure. You notice there are two blood pressure here ones. One has multiple categories. The other one is, once again, a binary, a 0, 1. And so I'm going to use the binary one and see if they tell us a little bit about predictability. Here's the null hypothesis. We're never really testing null. We're always testing the H1, the alternative hypothesis, to see the likelihood of that existing, because that's the false positive we want to guard against. And we find that, I'm going to add one more thing to this. I knew one more thing I didn't mess up. We need to know the standardized coefficient. This is kind of important, so you want to pay attention to this one. We want to get the standardized coefficient and the odds ratio. And we'll talk about that in just a minute. And so we're trying to use gender, and if you've ever had high blood pressure, to predict whether you've been booked into jail or not. First off, we check to see if it's significant. And it uses chi-square as its statistics, and yes, it is significant, 0.004. So we know it's a significant function. When we look at the significance level down here, over here, it uses what's called a wall test, but basically that's a probability test. And we find that the p-value for gender, is less than 0.05. The intercept is not significant. Nothing else is significant. The interaction of sex and gender, gender and blood pressure is not significant. The blood pressure itself is not significant. None of these are significant except for gender. Yeah. Gender is male, female, I believe. In other words, 1 is male, 2 is female. Correct me on that if I'm wrong. I don't have that code book in front of me, and I don't want to search for it right at the moment. Because it'll make a big difference.
Yes, the IRX sex is male or female.
Yeah, so it's male, female. So male is 1, female is 2. And when we look at this, we say, okay, this is significant. It has an odds ratio of 0.273. Now, we only look at odds ratios greater than 1 because odds ratios are a directional thing. They go from the static state or status quo to the experimental state, let's say. And so we're wanting to know what is the likelihood that being male would predict you also being booked. The fact that the odds ratio is 0.273, less than 1, tells us that no, that's not it. That gender really, even though it's a significant predictor, it doesn't really define for us the likelihood of males being more likely to be booked. Now, why is that the case? Because as you go from male to female, what's the likelihood of you being booked? As you go from male to female, what this less than 1 odds ratio is saying, the chances of being booked go down. We don't know how much. But we know the chances of being booked go down. Now, if we reverse the scales there, if we had made booked 0 and not being booked 1, we would probably have seen an odds ratio of greater than 1 that would have said, you know, males are more likely to be booked. But because of the way the scales are here, logistic regression is always directional. As you go from one level of whatever the predictor is to the next level, what happens to the outcome variable or the predicted variable going from status quo to experimental? But all you have to remember here is if odds ratio is less than 1, then you really can't talk about likelihood. So how do you figure out what's going on here? Well, just like everything else, you can run a follow-up test. In this case, it'd be chi-square, and we'll do a quick little contingency table here in which we put sex in the columns and booked in the rows, and we add in the expected values into the table, and we discover that we expected males to be booked 68 or not be booked 68% of the time. They were actually booked, or no, excuse me. We expected 68 males not to be booked. Actually, 57 weren't booked. We expected 33 males to be booked. Actually, 45 were booked. We expected 29 females to be booked. Only 18 were. We expected 60 females not to be booked, and actually 72 were. So, and this is a significant chi-square, which we know because it would be the same up here. Notice the p-value is identical, or should be close to being identical. Where's it at? 0.001, less than 0.001. That would be the case, always be the case. But what we really know from this is that high blood pressure doesn't tell us anything. Gender predicts for us whether you've been booked or not, and from an examination of the relationship between gender and having been booked, we would come to the conclusion that males are more likely to have been booked than we would have expected, and females are less likely to have been booked than we would have expected. Now, obviously on the exam, on the evaluation, I'm not expecting you to do this second part, this follow-up. But I am expecting you to say, okay, what's the chances up here? Well, it is that sex is going to predict whether you've been booked or not. We can't really use odds ratio to attach a likelihood to that, but we know that sex is a predictor of whether you've been booked or not. Now, here's the trick about why logistic regression is so much a good resource when you have categorical variables. And I actually had an article published, actually going to be in a book chapter, that we started with what are called continuous variables. We had data points, a lot of data points, and a lot of variation in it. But we didn't, we took a look at it and we realized that it was not a normal distribution. It was a very unusual distribution. And so we converted it to a binary variable, categorical variable. And one of the people critiquing the article the first time said, you never do that or whatever. And so I went back in and pulled up my resources, a couple of people that he had no clue about, that said that you can do that. You seldom ever do, but you can do that if you have some strange distribution going on. And so sometimes it's logistic regression lets us look at things that are not normal in different ways. And you can put as many predictors in as you want, given you have a large enough N. You need about N of 15 or 20 for each predictor. And so you could have 3 or 4 predictor variables in, and you could use it to sort out those things that aren't related and focus strictly on those things that are related. And so that's the nature of logistic regression. It's a very powerful technique. And with the other example I gave you in this example, hopefully it'll make some sense to you. Now I will put this, I'll rename this data set here as chi-square and logistic regression, and put it up on As You Learn with the the output and all it in there. Once again, as kind of a guide that you can use.
Dr. Bolt?
Yeah.
In the example that you had online for us, you were using a logistic regression regarding high blood pressure and something else. I forgot what it was. High blood pressure and sex is whether or not it can be predicted whether somebody would be obese. And in your example, you determined based on the logistic regression that high blood pressure had an impact on that. And you said that the odds ratio can be used to predict, in this particular example, the odds ratio for high blood pressure, it had a Z number of 2.76 and the odds ratio was 3.257.
Right.
But you said that the blood pressure, that people with high blood pressure were 2.76 times more likely to be obese. So use the Z factor as determining the likelihood? Or are you
Yes, I
supposed to use
did.
the odds
If I
ratio?
did, I used the wrong thing. Should be the odds ratio.
So that odds ratio number tells you the predictability of
Well, it tells you, what it tells you is the likelihood. You know,
the
what are the
likelihood.
odds? And so, you know, a person, what's that number that was the odds ratio? I don't know how.
The odds ratio is 3.257.
Okay. The odds ratio itself, 3.257, would tell you that someone with high blood pressure is 3.5, whatever, 27 times more likely to be obese than somebody that's never had high blood pressure.
Okay.
That's what the odds ratio. I don't know how I screwed that up. I think I screwed that example all up. So hopefully this is a better one.
So when we're looking at choosing whether to use the chi-square or the logistic regression to answer questions, you showed us how you can use kind of both to address questions. How would you know which direction we want to go in?
Well, you know,
I guess I'm confused as to which is answering what.
Yeah, okay. The chi-square is only going to tell you if they're related.
Okay.
It's going to tell you. It's going to tell you if they're related or not. You'd still have to go into the contingency table to figure out, you know, kind of what's going on here, what's not happening as we expected, what's happening different. You know, you'd have to kind of really kind of immerse yourself into the data. If you run a logistic regression, what it's going to tell you is that, okay, not only will we find out what predictors are significant, what are significant predictors, and part of the beauty of it is you can put several predictors in there, and it looks at each one of them independently, independent of any effect from the others. And so it will allow you to identify which predictors to look at. And the odds ratio, if it's greater than 1, allows you to attach, you know, an odd to it, an odds to it. And so if the odds are, you know, if the odds ratio is we'll use that example, 3.527, essentially it's saying the odds are 3.5, we'll round it off, 3.5 to 1, that a person with high blood pressure is going to be obese. You can convert odds back to probability. There is a formula. In fact, there's a resource that I put up on, that's up on As You Learn, that's talking about all about odds and odds ratios. And it's from a medical journal, so you know it's kind of using the medical language a little bit in it too. But it talks about how to convert back, you know, from odds ratio to odds to a probability. And so whichever you might feel is, you know, let's say it was 4. Let's say the odds ratio was 4. That means somebody's 4 times more likely. Well, that means the odds are 4 to 1. So the likelihood somebody that's has a high blood pressure would be, since it's 4 to 1, would be 80% more likely to get to be obese than a person that doesn't have high blood pressure.
Okay.
So see, the 4-to-1 equates to an 80% probability on the 4 side.
Okay.
Now, once again, these are likelihoods and probabilities and odds that are built around aggregate data. So they don't define individuals. They define the likelihood of an individual to have a certain outcome.
Mm-hmm.
And so, I don't know, I was watching a movie the other night. If you haven't seen it, it's, what is it, Burden of Proof? Yeah, I forget, but it's the one about Ruth Bader Ginsburg. And in there, early in her life history, she's married, and they're both getting ready to finish law school or getting close to finish law school, or he's getting ready to finish and she's not. But he's diagnosed with, and this is back in the 50s and 60s. So he's diagnosed with a particular type of cancer, and they asked the doc, what's the chances? And he said, well, it's only about 5% of males survive this. So his odds are 1 to 20. He lived to be, 75. So, the odds simply tell you in a group of people, if you had a group of people that all had your conditions, whatever those conditions were, 80% of them would be obese and 20% wouldn't. It doesn't tell you that you would turn out one way or the other.
Right.
Yeah.
So in these examples, you would probably start with a chi-square to see if there's actually a relationship. And then if the p-value is less than the 0.05, you can say that there is some type of a relationship existing.
No,
and then would you follow through with the logistic regression to see what's going on?
I actually work the other way around because, instead of going through, and once again, it's that the reason that we can't do independent t-test when we have more than 2 groups, because when you start doing all the 2-group comparisons, when you actually have an independent variable with 4 or 5 levels, you run up the error rate because each one of those tests has a 0.05 error rate. If you do the logistic regression and say throw 6 variables in there that you're interested in to predict a binary outcome, a yes or no outcome, one condition or the other, live or die or have something or not, then you can, under one test, find out which one of these 6 or 7 things are worth paying attention to, see if there's any odds ratio information there, and if not, then you can go back and do sort of chi-squares or something like that to see what's going on with each individual one. But it allows you to look at a whole bunch of different variables, pretty much all at the same time, different predictors all at the same time. And so it's a very efficient way of getting into an analysis if you've got a whole bunch of predictors that you think might be involved there.
Okay, thank you.
Yeah. Other questions? Okay, I'm getting rid of the share. Now, coming back in next week, what I want to do next week, once again, is for you to kind of work through all these things. Do some other analysis on this data set or different data sets, and who knows, if you get lucky, you might zero in on the one I ask on the final evaluation. I don't know who knows. But try some of those things just to get a little bbit more familiarity with chi-square and logistic regression, correlation, t-test, all that, so that you kind of have a sense of what you do when. Now, I always give you a clue. I always say, hint, independent, and I'll put a hint on it so that I won't let you run the wrong test unless you just decide to ignore the hint and run it anyhow. But, you know, that's up to you. But, you know, what we'll do is between now and then, you might kind of run through some of those things, see what happens. You know, try an ANOVA on this data set, you know, go back and pull that ANOVA out that didn't work real well and try it on this one and see how, you know, what you get to. And then ask all those questions next week. Ask them all. And all these other little topics, if we don't get to them, I'll put them in a video. I'll post a couple of videos. But, you know, just have all these questions in hand, and you can take a look at the final exam. It's right there. And, you know, as I said, the only question I won't knowingly answer is one that's specifically related directly to an evaluation question. Now, I might get close unwittingly, and so I might have to check myself every now and then, but. Anything else? Any other questions? All right, I will put this JASP file up, you know, with these couple of examples in it, and it'll be titled chi-square and logistic regression on final data set or something like that. And so you'll know where it's at, but I'll put that up and then I'll get the videos up as soon as they go through all their transformations. Otherwise, you know, have a good week, play with some things, and I'll do another, as I said, help session next week. If you have particular individual questions, you know, email me, you know, if we need to go face to face, we will. But, you know, let's ease into this final evaluation so that you don't have any redos. Make my life easy.
Ours too.
All I have to read is 4 other 50-page projects. You know, I thought it was a good idea to allow another class to work in teams until I kept thinking about how big the project was growing. It turned out to be about 50 pages for each team. So another idea that didn't pan out exactly the way I thought it would, but I got to read them. So. Okay, guys. Well, y'all have a good evening and have a good week. And if you have, stay safe. By all means, stay safe. And if you have, you know, any troubles or anything, just give me a yell.
Okay. Thank you very much.
Thank y'all.
Take care.
Have a good night.
Bye-bye.
Thank you.
Thank you.